The rate of a reaction is affected by different factors. Some factors are chemical nature of reactants, concentration and surface area, temperature, and catalyst. Chemical nature of reactants. For any reactant, the bond type, bond strength, and bond number determine the activation energy required for a successful collision. If fewer bonds per reactant are broken, the reaction is faster. Weaker bonds are more easily broken, so they break at a faster rate than stronger or rigid bonds. For example, it takes less energy to break a carbon-carbon single bond than a carbon-carbon double bond. The size and shape of a molecule or ion also affects how fast a reaction goes. Concentration. When the concentration of a reactant is high, the probability or chance of collisions or collision frequency between reactant molecules is greater. If there are more reactant molecules, it is more likely they will knock into one another. Thus, more effective collisions could occur. The reaction rate therefore increases. Surface area. In a reaction involving reactants in more than one physical phase, say a solid reactant and a liquid reactant, increasing the surface area of the solid reactant increases the reaction rate. Particles that are clumped together in a solid have fewer potential collision sites, as only the outer exposed surface area is available for reaction. When a solid is broken up into smaller pieces, the total surface area increases, increasing the number of possible reaction sites and increasing the rate of reaction. What is the connection between energy, rate, and temperature? For most chemical reactions, reaction rates increase exponentially with temperature. An increase of about 10 degrees Celsius often doubles or triples the reaction rate. When temperature is increased, the average kinetic energy of the particles increases. As a result, more reactant particles have enough Ke to break bonds and form an activation complex. The increase in Ke also increases the rate and force of collisions between reactants. This means that the chances of achieving effective collisions are higher. Temperature changes. The diagram shows two graphs, one red and one blue. Both are the Maxwell-Boltzmann distribution curves at different temperatures. The vertical dotted line represents activation energy, EA. The blue line or blue curve and the area beneath it represent a collection of particles at a lower temperature, T1. The red line or red curve and the area beneath it represent a collection of particles at a higher temperature, T2. But what do the curves mean? At the lower temperature T1, only a small number of reactant particles move with enough energy to collide forcefully and undergo reaction, which the number of reactant particles with kinetic energy matching or exceeding activation energy are represented by the point of the activation energy dotted line touching the blue curve, the points on the dotted line beneath the blue curve, as well as the area to the right of the dotted line beneath the blue curve. The region under the blue curve to the left of the activation energy dotted line represents the sluggish reactant particles that don't have what it takes to undergo reaction. At a higher temperature T2, more particles have enough energy to overcome the barrier, that is, activation energy for effective collisions. The shaded area below the red curve represents the extra number of reactant particles that can undergo successful collisions. So for the red curve, the number of reactant particles that can undergo reaction is like that for the blue curve, plus an extra number, the ones in the shaded region. Thus, when temperature is increased, there is a greater number of particles possessing kinetic energy that is greater than or equal to activation energy, EA, to undergo reaction. Catalysts. A catalyst is a substance that increases the rate of a chemical reaction without itself being consumed. A catalyst actually undergoes reaction, but it reforms after the reaction. What are the characteristics of catalysts? Each catalyst works in its own specific way. A catalyst speeds up a reaction by providing an alternative pathway with a lower activation energy, EA. A catalyst does not increase or decrease the overall reaction yield, that is, amount of product formed, but it allows the product to be formed more quickly. A catalyst is not used up, rather it is used and regenerated. Here is a comparison of the activation energy barriers of an uncatalyzed reaction and the same reaction with a catalyst. A catalyst provides an alternative pathway with a lower activation energy, EA, but does not affect the energies of the reactants and products. Note that we cannot say that a catalyst lowers the activation energy of a reaction. Rather, a catalyst provides an alternative pathway or a different route for reactants to take. In this new pathway, the activation energy is lower compared to the original pathway without a catalyst. Here is a reaction energy diagram for a catalyzed and an uncatalyzed process. When activation energy EA is relatively low, such as in a catalyzed reaction, a greater number of reactant particles can undergo successful collisions since more of them have kinetic energy equal to or greater than this low activation energy. In contrast, when activation energy EA is high, such as in an uncatalyzed reaction, fewer reactant particles have enough kinetic energy that is equal to or greater than this high activation energy. This is like different schools with different passing marks for a math test. In school A, the passing mark for the math test might be 80 marks. In school B, the passing mark for the math test might be 50 marks. Fewer students in school A are likely to pass the test since the bar for passing is set higher. In contrast, more students in school B are likely to pass as the bar is lower. Heterogeneous and homogeneous catalysis. The prefix hetero means different. In heterogeneous catalysis, the reactants and catalysts are in different phases. For example, in Haber synthesis of ammonia, which is used as a fertilizer, the catalyst ion is in solid phase, while the reactants are in gaseous phase. That is, the catalyst and reactants are in different phases. The prefix homo means the same. In homogeneous catalysis, the reactants and catalysts are dispersed in the same single phase, usually liquid. Examples: acid catalysis and base catalysis in aqueous medium. Examples of homogeneous catalysis. An example is the oxidation of sulfur dioxide to sulfur trioxide with the catalyst nitric oxide. This is the lead chamber process for the manufacture of sulfuric acid. The symbol G stands for gaseous phase. It can be seen from the equation that the reactants, sulfur dioxide and molecular oxygen, are in the same phase as the catalyst nitric oxide. This is a gas phase reaction. The rate of a hydrolysis reaction of an ester is slow at room temperature, but is greatly increased by adding a small amount of strong acid, which provides H+ ions. Example: in acid catalyzed hydrolysis, the reactants ester and water and the acid catalyst are in the same aqueous medium. Examples of heterogeneous catalysis. The catalyst is usually a solid interacting with gaseous or liquid reactants. A catalyst usually has an enormous surface area for contact. An increase in the surface area increases the rate of reaction. Many reactions occur on metal surfaces. Decomposition of gaseous hydrogen iodide on solid gold and decomposition of gaseous nitrous oxide on solid platinum are examples. In both examples, the catalysts and reactants are of different phases. Another example of heterogeneous catalysis is the addition reaction of hydrogen gas to carbon-carbon double bonds or carbon-oxygen double bonds to form single bonds. Petroleum, plastics, and food industries frequently use catalytic hydrogenation. The conversion of ethene gas and hydrogen gas to ethane gas is slow without a catalyst. But in the presence of finely divided solid nickel, platinum, or palladium, the reaction speeds up. Enzymes are biological catalysts. Enzymes in humans, animals, and plants speed up many important chemical reactions. These enzymes have unique shapes and invite reactant molecules or substrates with appropriate shapes to react with them to eventually generate products.